The most important equation in quantum mechanics is undoubtedly the Schrödinger's equation. So far, I have never seen anyone prove it before, whether if it's in a textbook or an essay. The only thing we can do right now is just blindly accept that it exists. Being the curious one that I am, I set out to make a full proof. And I think I did it! In one of Schrödinger's speeches, he talks about how all matter has its own wavelength. Every type of wave, water, guitar plucks, electromagnetic, have its own differential equation describing it. Except for quantum waves. A physicist named Peter asked Schrödinger, why don't electrons have their own wave equations? Schrödinger pondered for a while and replied, I'll be right back. He ran back home and started the quest for the electron wave equation. He flipped through many documents. He thought deeply for a long time, but no ideas popped up. Ah, screw it, he said. Schrödinger took a beautiful girl out to the beach to spend a romantic night together. Let's call her Emily. Alright, after staring into the sea while holding hands, he pinned Emily onto a wall and brought his lips closer and closer. Oh, Schrödinger suddenly has a bright idea. He sprints out to a rock nearby and carves the following equation, leaving Emily dumbfounded. Now, let's see his derivation in quantum mechanics. First off, in order to understand this derivation, you need to know these things. The Hermitian conjugate, defined as follows, where the dot product of psi with a phi equals the dot product of a Hermitian psi with phi. Here, AH is the Hermitian conjugate of the operator A. Alpha dot beta is part of bracket notation, representing the dot product. We've covered this in the last episode. Next, the definition of a unitary operator, where u to the negative 1 denotes the inverse of u. Lastly, the Taylor series centered at A, where psi to the parentheses k of x denotes the kth derivative of psi of x. Let's get proving. Suppose that u of t is unitary and reversible, and the time involves a quantum state psi naught by t seconds. First, we need to Taylor expand u of delta t acting on psi naught. Recall the Taylor series at a equals 0. Here, we're only using the terms up to degree 1. All of the remaining terms will be written as O of x squared. Plug in x equals delta t. As delta t approaches 0, we get the definition of the derivative of psi of t at t equals 0. We're going to use this later on. Consider the following, which is true by the first statement. Plug in t equals delta t and Taylor expand, which should give you something like this. Let delta t approach 0, and we get that u of 0 times the derivative of u Hermitian of 0 equals negative u prime of 0 times u inverse of 0. Because u of 0 and u inverse of 0 both equal the identity, we get that the derivative of the Hermitian of u at 0 equals negative u prime of 0. Consider this expression, I times u prime of 0. We can show that it is Hermitian by the third statement. We get that I times u prime of 0 equals q psi for some Hermitian operator q. By the second statement, we get that I times the time derivative of psi equals q psi. Let h equals h bar q, where h bar is 6.63 times 10 to the minus 34 joule seconds, and we end up with a time-dependent Schrödinger's equation. The operator h is called the Hamiltonian, and it is the quantum analog of the total energy, where the total energy equals 1/2 mv squared plus the potential function. T and V represent the kinetic and potential energy, and P is the momentum operator. So, this says something exciting. to look at the energy of a quantum particle. We keep track of how the quantum state changes with time. The more I learn about quantum mechanics, the more strange things I find. But there's a similar thing in our everyday scale, called the Lagrangian. We've covered this in episode 4. The rate of change in Lagrangian is related to the total energy. So, what is the conclusion for today? Don't put your head down when you're stuck trying to solve a difficult problem. Instead, bring a pretty girl to your nearby beach to